Alright guys, this last video is going to be about transformers, how they work, how we can kind of calculate things, kind of some of the ideas behind them. And like I said, we'll go from there, and this is the last video that we're going to have for this topic. So with that being said, that should give you everything you need to do to get through all the quizzes, the homeworks, the assignments, that kind of stuff. And as always, please feel free to ask questions. If you have a question specifically about a spot in the video, let me know the times and all that stuff, and I will address your questions and whatnot. And as always, get a hold of me whichever way you need to, text, call, email. I'm available and here for you guys. So the idea is with transformers. So this is the schematic symbol for a transformer. Most of the time they're going to look like that, and because that's going to be the core of the transformer. So now what a transformer is, a transformer, I guess I could probably make that a little bit nicer. So a transformer is simply two or more inductors or coils that are close enough for each other to have their magnetic fields induce a voltage in each other. So the coils are close enough to induce a voltage in each other due to their magnetic fields overlapping each other. So now the reason that how this works is, so in a transformer we have two areas of the transformer that we're going to talk about. So we have a primary side and we have a secondary side. Now, depending on how these are made, they're going to have different ratios and things that we're going to talk about and how they work. But the idea is we energize one side of the transformer, which we'll call the primary side, and then the secondary is where we're going to take the output. Now, how these guys are set up, they're going to do a couple of things, and one thing they're always going to do, they're going to isolate DC from each other. So it's a nice way to separate and clean out any DC that gets into signals, filters it out, that kind of stuff. It'll only transmit the DC or the AC portion of waves. So it's an isolation device for one. And two, we can use it to either step up or step down AC voltages. It makes it really easy, really simple. If we only have, like our generators that we have on our scopes, they put out a maximum of 2.5 volts peak. So let's say we wanted a 6-volt signal out of this guy. Well, we could use a step up transformer and we could step that signal up to 6 volts, which then gives us a better opportunity to use those. So that's another option that we have to use, is actually using those transformers to step up the voltage to get a wider range of signals. So, and it's all based on the magnetic field. So on our primary, when we energize it, it's going to create magnetic fields. So let's go ahead and kind of draw this and explain it right now. So if we take our transformer, we hook it up to a signal, has two inductors going over to some load or whatever. So what we do is when we start flowing current, we start running our AC current through this guy, what we're going to do is we're going to start generating a magnetic field around this inductor. Well, in turn, what's going to happen is this magnetic field is going to swell and decrease and collapse and generate, and it's going to be changing. Well, this secondary coil over here, this is going to be picking up those magnetic fields, and in turn, it's going to induce a voltage, which now is going to allow a current to flow this direction, and it's going to ebb and flow according to how the primary is doing. And so in the instance, we're going to get a copy of whatever signal is coming from this primary source, but it electrically isolates them. So anything that we do over here is not going to affect this primary at all. We're just going to be taking a portion of it, using it, and doing whatever we want. So it's kind of nice because, again, it isolates our system from our power generation. It's one way we can use to protect ourselves, from power surges. From if we short something out over here, it's not going to cause an issue over in our primary, which is really nice for certain applications. So when things happen, we have a way to kind of protect ourselves from them. So one of the things that we need to talk about is, so that's this idea here, is this magnetic field being shared and inducing a voltage into another one. This is called mutual induction. So it's basically when we apply the properties of an inductor, how it generates a field, and how we use Faraday's law with a coil that passes through a magnetic field, or a magnetic field passes through a coil, it induces a voltage. So that's what this comes from. This mutual induction is the property by which transformers work. So one of the things we need to understand about a transformer is we have to understand what a turns ratio is. This is the big key for a transformer as far as what they do. So we have a turns ratio. So what this is simply, it's the physical number of turns between the primary and the secondary coils. This translates into how much voltage is transferred. Is it stepping it up? Is it stepping it down? So the idea behind this is it's a direct relation. So for example, the ratio that we have is the number of turns in the secondary over the number of turns in the primary. That's going to give us our little n, which is the number of the turns ratio. So if we have, let's say we have 100 turns in our primary, we have 400 turns in our secondary. This means that we have a 400 over 100, or we have a turns ratio equal to 4. Another way to look at it is we have a 1 to 4 ratio. So what that means is for every one winding we have on the primary, we have 4 windings on the secondary. And that directly translates into how much voltage that our circuit is going to have. So if we have, with this transformer setup right here that we have with 400 in our secondary, 100 in our primary, with our turns ratio of 4, 1 to 4 ratio, that means if we have 1 volt in our primary, we're going to have 4 volts in our secondary. Now, the inverse is true. So if we have, let's say, 400 turns in our primary, we have 100 turns in our secondary. We look at the ratio. So we're going to have 100 over 400 is going to give us our turns ratio, which is going to reduce down to 1 over 4. So this is now a 4 to 1. So this means if we have 1 volt in our primary, we're going to have a quarter of that, or 0.25 volts in our secondary. So this directly correlates to how we do that. And there's different configurations that we can run based on these guys. But the biggest part here is our turns ratio, is what is this ratio set up to be? Is it a step up transformer? Is it a step down transformer? Or is it a 1-to-1, which would be an isolation transformer, which we do have those. So this is a step up. This one is a step down. And this is an isolation. So 3 different uses that we have for transformers. One of the things that we have in a transformer is the power is going to stay the same. So the power that we produce in our primary, and I am dyslexic. The power we have in our primary has to equal the power of our secondary. So that means if we have, if we have 1 volt and we're flowing 1 amp, that gives us 1 watt of power. that means we have to have 1 watt of power in the secondary. It's the conservation of energy law. We can't just create power, we can't just lose energy. It has to be contained throughout the whole system. And because of this ratio right here, and because of this law that we have, the conservation of energy, the power has to remain the same. So if we look at this guy, so if we have a step down transformer, so that means it's a 4-to-1 ratio or whatever it may be. So that means our voltage is going to go down by 4 times. That means our current is going to go up by 4 times because we have to maintain this relationship. If we have a step up transformer, so if we have a 1 to a 4, our voltage is going to go up by 4 times. Our current has to go down by 4 times. And then, so once we have that understanding of that the power has to stay the same, so these two are going to be changing. We increase our voltage, we have to decrease the current. If we decrease our current, or decrease our voltage, the current has to go up. So maintaining that, we have a couple other ratios as well. So we have the turns ratio is equal to the number of turns in our secondary over the number of turns in our primary. Our turns ratio is also equal to the voltage in the secondary over the voltage in the primary. So that's another way we can find out what the turns ratio of these guys are. And then the last one we have is our turns ratio is the current of the primary over the current of the secondary. Now the reason that these guys flip is because of this inverse relationship between voltage and current. So as the current, the primary current goes up, the secondary current is going to go down. And that, like I said, this is going to be how we're going to follow these. These are going to come into play here in a little bit when we start talking about how to get some of these calculations. So with that before, we have different kinds of transformers. So that's kind of the basics understanding of how the transformer works and why it does what it does. We step up the voltage, we step down the current. If we step down the voltage, we step up the current because power has to maintain throughout the entire system. So now that we have these kind of the equation set up, the ratio set up, and a very basic understanding how transformers work, then that's all they are. They're just 2 coils of wire. We energize one, it induces a voltage in the second one, and then we can use that voltage, and it's just based on what our turns ratio is on how that works. So now that we have that done, we need to look at a couple other things. So we have the different types of cores, just like what we have with an inductor. So if we have our transformer here, and it doesn't have anything in between its 2 coils, this is said to be an air core transformer, just like we have air core inductors. So it's just the coils are wrapped around like a cardboard tube or paper tube or something like that. That's all there is. Just like with the inductors, we have our coils, and if we have 2 solid lines between them, this is an iron core. And then if we have dashed lines, this is ferrite magnetics. And so the reason that we use different cores is it enhances the signals. It either boosts the signals or it degrades them. It keeps them closer together, so the coils have to be really close together, or it expands them out so they can be a little bit farther apart, to be able to dissipate more heat or things like that. Just individual properties is based on what they use for them. It doesn't really matter to us right now what type of core it is. They've already been tested. We're not building one, and so what they say is what they're going to be. It doesn't matter what type of core it is, so they might have just slightly different distances between the inductors or things like that to accumulate for all the materials that they can make them out of. So now that we can understand, at least this is what our schematic symbols are going to read, so we can identify what type it is. And just kind of as a note, that's one of the questions on the quizzes, is to determine what type of a core is this transformer. And it's just something to note, because sometimes you'd be in situations where you can't use a magnetic core. So you have to make sure you have a transformer that is not made out of ferrite. Iron may be questionable because you can create a magnet at that point with a coil of wire. So in those instances, you'd probably just want an air core if you couldn't have anything that was magnetic. So kind of things to kind of be aware of in the applications of why do we have the different types of cores, and then that's how we identify what they are. So one of the other things that we do is we also have to kind of look to see how is my load transferred or reflected back to the primary. So we have to take that into account. So if we have, and like I said earlier, it isolates it, but it isolates the signal, but it's still going to see something to it. So if we have our transformer hooked up to a signal like this, in all honesty, to this signal, it doesn't care what everything else is. It wants to look at one final value to simplify it down in terms. So what it's going to see, and I use that very loosely, quote unquote, see, is just this. It's going to see just the value coming across this. And the way that we have to look at it is there's going to be a little bit of a conversion. And because, like I said, because it only cares about what we're using in the end, what it sees, we're going to condense everything down. So the way we look at this is we got to look at kind of these ratios again. So we have our R load for the primary. This is what we're trying to solve for. What does the source see when we connect it up to this circuit? And we put that over the R of our secondary. So this here, remember, this is our secondary, this is our primary. So what we're trying to see here is our R primary, and then this is our R secondary. Okay, so when we look at that, well, how do we get our resistance? Okay, think back of Ohm's law. This is kind of going back to what we talked about before. How do we get resistance? We take the voltage divided by the current. So we have the voltage of our primary divided by the current of our primary. The other part of the ratio is our secondary is now voltage of our secondary divided by the current of our secondary. So now, and the reason we're going through this is just kind of see where, you know, we can solve for these things. We don't have to go through this entire circuit to solve for it. Like we could have our transformer, we could have several resistors, we could have a couple capacitors, inductors, whatever it is. We could just run through this formula to determine what is this guy going to see against everything. So, like I said, this will all simplify out here in just a second. We'll use this here once in a while to kind of understand real quickly what is my source seeing, what kind of a load am I putting on this source, so we can use it to impedance match. That's going to become important, really important in fourth semester when we get into the RF, and you'll be seeing other times where we want to match what our input and our output are seeing, because that's going to give us the most amount of power. This is where we get into the maximum power transfer, which we've talked about briefly at times throughout the semester. And where this is our input matches our output. That's going to give us the most power on our output. So if we have more resistance on our output than our input, we're going to see, a decrease. And what it's going to be more of like a bell curve. So right here in the center of this, if we're looking at this curve, this represents power, not an R. This represents our power. This is, our resistance or whatever. What we're going to see is here, we're going to have the most power. So power is going to be greatest at our load and our in are equal to each other. That's when we're going to have the highest amount of power. So that's kind of where this idea comes from, is we're going to be using it to matching impedances and things like that. So anyway, so getting back to our formula to kind of understand this is we want to see what is this source seeing, so we can kind of match things up as we go. How much resistance is the primary going to have all that kinds of things to get these equal. So we have our equation here. Well, now we're dividing. Division of fractions, we want to convert it into multiplication of fractions. It makes life easier. So we're going to take this guy, we're going to invert and multiply. And so this now becomes our R primary, which is the value we're trying to solve for. Usually we know what we have on our load for our secondary. So we're going to have V primary over I primary. That's now going to be multiplied by our I secondary over V secondary. Now, one of the things we need to remember as well is now that we're multiplying, we can change the order of these as we want. We can kind of separate them up. Now we want to look for ways to simplify this equation down into terms of that we have, so we don't have to go through and solve what's my voltage, what's my current, all that kind of stuff, because right now this isn't helping us. So if we go back and look, okay, we can go back and look at our original ratios. So we have our N, which is our turns ratio, is equal to the voltage of the secondary over the voltage of the primary. We have N is equal to the number of turns in the secondary over the number of turns in the primary. Then we also have is the current in the primary over the current in the secondary. So when we look through at those three equations, to try and simplify this down into terms that we know, the N that we get is usually given to us in the data sheet of our transformer. So this value we know right off the bat. We'll know what kind of a load we're putting on because we're putting it on there. And so we want to kind of see what our primary load is. So in this case, we can recombine these guys to start making some of these equations and get it in terms of what do we know? How can we substitute in things that we don't know for what we do? So we end up with our R primary over our R secondary is equal to V primary over V secondary. Because this is all multiplication and division, I can swap these guys around. And this is multiplied by our I secondary over V secondary. I secondary. We're combining things together. So if we come over and look back at our original ratios to get these back in terms of what do we know, just like what we were doing with the universal shunt meters, what do we know, what don't we know, things like that, we can come back and look and be like, hey, look, we have voltage primary, voltage secondary. Hey, look, we have one here that's voltage secondary over voltage primary. Okay, well, how does that help us? Well, if we take the inverse, so if we take all these guys and we invert it, we get 1 over N is equal to the voltage of the primary over the voltage of the secondary. All we did was invert it, so we're maintaining our math and maintaining the functionality of these guys. So if we do that to all of them, we end up with N of the primary over N of the secondary. Doesn't really help us out a whole lot because we're not dealing with the number of turns. But the last one, if we take the inverse or the reciprocal of it, we end up with the I secondary over I primary. Just how can I manipulate things around to get, to start eliminating things. So we have a V primary over V secondary is equal to 1 over N. Hey, we can swap that in there. I secondary over I primary is another one. So now when we look at it, we can reduce this down. So we have our R primary and our R secondary is equal to 1 over N times 1 over N. And N is a value that we can get, and that's not going to change on our transformer, which makes it really nice. So now we can combine these guys together. So we have R primary is equal to 1 over N quantity squared. And that's our primaries over our secondary. So again, we're trying to solve for what is this our primary? What is our load, or what is our source seeing when we connect in the load? Well, we know what this value is, so we can bring it across, and we're just trying to solve for this guy. So our R primary is equal to 1 over N quantity squared times our R secondary. So basically what that translates into, and then this comes out to be our final equation. So now we can find out what is my primary going to see, but I'm not going to have to do any conversions. It's one quick, real fast equation to solve for what I need. So in this, let's look at a circuit. I have my transformer, and I have a 2 kilo ohm load attached to it. A motor, a light, whatever it may be, we have it attached. And I want to know what is my source. I want to simplify this down to just what is my source going to see. Doesn't know what it is. So this is our secondary. And let's say our transformer is rated from a 1 to 5. Okay, so it's a step-up transformer because it has 5 times as much on the secondaries as the primary. So our N, remember, is N secondary over N primary. So it's 5 over 1, so N is equal to 5. Okay, just for example on this guy. So we're going to say this is stepping up the voltage. We put 1 volt in, we get 5 volts out. That's how to think about this. Okay, we want to see what just this guy is going to come up with. Okay, so instead of having to solve for the voltage of this, solve for the current, translate the current back across to here, and then solve it that direction, we can just simply put it into this formula, and we know, okay, if I have this transformer and this load, this is what I'm going to see, and I want to try and get those to match. You know, if I put resistance or other things in there to get everything, so we get the most power out of it. So this one we have 1 over 5 squared times our initial resistance. So when we run that through in our calculator, so we have 1 over 5 quantity squared, multiply that by our original value. So that means what this source is going to be seeing, our primary, is going to be seeing 80 ohms. So that works out really good because a lot of the generators we have, if you take a look at the sheets of them, the data sheets, or even it's printed right on there, a lot of our generators, they come in, their input, they have the generator themselves has 50 ohms. So basically what we're doing is we're translating through the transformer, through our load. So our source is seeing 80 ohms. And in this case, the generator, it might be 50 ohms. So that means we're going to have a pretty good power transfer. We're not going to be losing a lot on the generator itself. We're going to get as most power we can to our load, which is where we want it. So in this case, they would match up pretty good. If we had the other direction, if it was a 5 to 1 instead of a 1 to 5, we would flip this around. This would be a 1 over 5, which would flip that, which would be 5 squared times 2K, which would take that up to 50,000 ohms. So, like I said, we can kind of see and play with this is, and the whole idea of trying to determine what our primary is what is the source seeing once we remove everything else from the circuit. That's kind of the whole idea. And like I said, it's just a quick equation to see what it sees. As far as that goes, we're going to use that a little bit once in a while. A lot for impedance matching is going to be the big thing. We're not going to do it a whole lot in first semester. It's just so you guys are aware of it when we get into it in the later semesters. Okay. So that's about as far as I'm going to cover on those. So the next part I need to cover about transformers is another thing you'll see on transformers is we have phase dots. Now the idea behind phase dots is like you guys have been seeing with the RL circuits, RC circuits, is different components put things in and out of phase. Sometimes we want them to happen first, sometimes we want them to happen later. So one of the ideas behind this is we can use a transformer to invert the phase of our signal. So basically it delays it by 180 degrees or half the time of a cycle. Because sometimes we want to do that deliberate. So let's say we turn everything on. We want everything to have a chance to fire up, have all the different circuits get energized before we start sending in a signal. Now, when we talked about diodes, remember, we can use it to clip off a positive or negative portion of the signal. So we could run this through a transformer, clip it off so everything has the time to power up. Well, we clipped off our signal, there's nothing, and then our positive signal comes in and fires everything up, and has it start doing its chore. It's one of the timing things that we'll use, and you guys will use it a lot in the advanced semesters. It's a timing thing. Computers, they all run on timing. Things have to happen at a specific time. Well, when you first power the system on, this gives you a chance to get everything in storage, loaded into the memories, loaded into the arrays, execute the setup codes, that kind of stuff, before you start giving a clock signal or a pulse or something like that to use later on down the line. So that's kind of the idea behind this. And sometimes, depending on, if you're using an amplifier, which you guys will learn about in second semester, this gives it a chance, you can invert signals without having to invert, your amplifier. You can use a method that one of the amplifiers you want to, and you just simply invert your incoming signal. So anyway, with all that being said, here's kind of the idea behind it. It's real simple. So we have our transformer, and we're going to say this is a 1 to 4 transformer. And when there's no dots or nothing in here, so like there's no dot there, no dot on any of them, you're gonna have 0 phase shift. So what that means is this is our primary, these are our output signals, so our V secondary. So we're going to see this type of a signal going in, and we're going to have 1 volt in. We're going to see this same type of signal coming out. Everything's going to line up. And then at the point here, at the peak, we're going to have 4 volts. So everything's in phase, everything's good to go. Now, if we have phase dots, so if we have a phase dot, it'll look like this. They're both on the top. So both of these translate into this same type of outform. We put in a waveform, we're going to get that exact waveform out with the transformation of whatever our signal is. And the other reason why we use these is this is how we decided with power generation. So when we generate power, it's in the form of AC. And that's how we can generate 30, 40, 50, 60,000 volts at a dam or a power plant or whatever. We send it down the transmission lines, and then when it gets to us, it goes through a series of substations, which is just a series of transformers where it steps it down from the 30,000 volts, steps it down to 5,000 volts sitting in there, and then you have one transformer before it even comes into your house where it converts it again into 120 that we use normally in our house. But it still has all that voltage sitting out on the line that can transfer everywhere that anybody can take that power off of. And so, and sometimes we have to invert things, and it just depending on our application. So these phase dots here is representative of those. So we have, if there's no dots, it's assumed to be in phase. If there is dots and they're on the same direction, up or down, then it's considered to be in phase. The other one we have is if they're out of phase. So if we have our transformer and we have 1 dot on the top of our primary, 1 dot on the bottom of our secondary, this has a 180-degree phase shift in it. So what this looks like is this is our V primary. We have a normal sine wave with 1 volt. And then what we're going to see, I'm just going to draw these lines so I can get these things to line up as best as I can. What we're going to see is when this guy goes positive, it's going to be at its negative peak. 0 is going to match up. This is going to invert and go back to here. So we end up with the waveform that looks like this. That's 180 degrees out of phase. So here is negative 4 volts. Here is negative 1 volt. And here is positive 4 volts. So we get 180 degrees out of phase. And like I said, this is where we would take on our output of our secondary. If we ran it through a diode, like that, it would clip off this negative portion of the waveform. And so then we would just have this positive peak that's going to happen after some amount of time to give everything kind of a chance to boot up and fire up and get all the systems going to what they need to be, and then they can start responding to the signal. In amplifiers, next semester you guys will see that as well. You'll be able to build an amplifier that you'll put in a sine wave and basically get a cosine wave out. You're going to have 180 degrees out of phase. And then you can control this, and this can actually be used to counteract that if all you can build for whatever reason is a inverting amplifier. You could put an inverting transformer in there to isolate your systems, split out the DC, keep the DC from getting out, and flip it back into the right polarity that you get, or the right phase, depending on how you're going to use it. And like I said, transformers, they will isolate DC. So if you put in a DC signal through a transformer, basically you've turned it into a coil like a relay. So it turns on and it builds the magnetic field, but once that field is established, you're going to see a little bit of induced voltage, but because it's not changing, there's not going to be any induced voltage again. You'll see a little spike and then it'll drop off, and then there's going to be nothing for the rest of it. So it's really good for isolating DC. Another thing that we need to talk about is how to, different configurations of the transformers. So if we have a transformer here, we can then put a center tap on this guy. So we're going to split this in half. So basically we have a 50% here, we have 50% here. We're going to label those points A, B, and C on our secondary. So we have a 1-to-4 transformer. So what this means is from the entire primary to the entire secondary, it's going to step it up by 4 times. So if we look, so if our voltage of our primary is equal to 1 volt, the voltage in our secondary from A to C is going to be equal to 4 volts. Because if we look, we're going across the entire secondary coil. So we're going to get everything. So if we take the voltage of our secondary from point A to B, when we have a center tap, it splits it in half. So what this means is we have 2 volts because it's only 50% of this. So what we end up with is here we have a 1 to 4 ratio. Here we have a 1 to 2 ratio. And then if we look in the V secondary, from B to C, it gives us 2 volts. And we still have a 1 to 2 ratio. And we can have multiple taps on a transformer. I was working on an arcade game recently. It was an old arcade cabinet of Space Invaders. We were trying to get it to work, and one of the things it had on there was this great big transformer with about 18 wires coming off of it. And we're like, holy crap, what is going on? So we looked into the schematic, and what it had was it had multiple, so it had a primary coil coming in, and then it had the secondary coil coming in. And like I said, there was like 18 different wires coming off, and so each one of these different sets had a different voltage. So it had like a black and a brown combination that was 15 volts. They had a purple and a green, and that was 10 volts. And then they had a yellow and an orange, and that was 2.3 volts. And so what it was is they just had multiple taps. So if you look, with this, how it would look in the schematic was it looked like this. Lots and lots of cables. So here was point A, here was point B, C, D, E, whatever. Different colored wires, black, purple, green. So this was like 10%, this was 5%, this was 15%, or whatever it was. And so you can split it up and even have multiple taps off of a transformer if you want to be able to have multiple voltages coming off of one single device. Because remember, it all comes down into cost. So it's cheaper to get one unit that has multiple outputs than one, or multiple units to do one output. You're looking at 3 or 4 times the cost. And so it's easier just to kind of do this idea of tapping off and taking a portion of it based on, where it is. But if it's a center tap, remember, it's always going to be in the middle. So it's going to be 50% above, 50% below. And if it doesn't give you any values and there's only like one line coming out of the center of it, assume a center tap. Just kind of as a rule of thumb. And so that's kind of the idea with the transformers is we can use those to get whatever values we need out of the transformer. We just simply tap into the coils, and all we're doing is we're just changing the amount of our turns ratio. So here, again, if we had, let's say we had 10 coils over here, we had 40 coils over here. So we had 10 coils put in, or 20 coils put in the center tap, then the other 20 coils, and now we've created this scenario here. On this guy or whatever, the one that I was working on, if, it had the same, so let's say we had a 10 to 100 or whatever it may be, we'd have 10 coils here, we'd have 5 coils here, we'd have 15 coils here, and then, see, that's 20, 30, then we'd have 70 down here for the rest, or whatever it may be. All the ratios are still going to follow the same thing. It's just taking a portion of the inductor and using it for whatever purposes that we need it to. So with that, that's kind of the basics and the basic understanding of how a transformer works. That's all it does, is it's just in creating a magnetic field. That magnetic field is inducing a voltage into a secondary coil, and then we can split up that secondary coil however we want and use it for whatever that we need it to. So kind of now to wrap things up, let's go through an example like what we would see in the homework. So the idea behind this is we're going to be given a circuit. We'll have an input and an output, basically a generator and a load, and we want to solve all the parameters across this guy. So our circuit is going to look like this. So we have a generator hooked up across our transformer. And the secondary is all together, and it's going to be going into a 1 kilo ohm resistor. So now, and we also have phase dots on there too, so that's something we're going to have to pay attention for. So the things we want to solve for this guy is we want to find what is our V secondary, what is the voltage across R1, so I'll label these guys R1, this is our V source, this is our primary, this is our secondary. We want to know the current in our secondary, we want to know the current in our primary coil, because transformers are rated in power, so you need to know how much voltage you're going to be pushing through it and how much current you're going to be pulling through it, and that's going to determine your maximum settings that you can use. And like I said, it's all based on power. So then we want to find the impedance of our primary. It's going to be the same as following with the resistance. We're just going to be using impedance now because now we have coils, we have capacitors, we have all sorts of stuff, and so the impedance is the catch-all for all those guys. We want to find how much power we have in the primary, which will be equal to the amount of power in the secondary. We want to know what the phase angle, if there is a phase angle or phase shift in the secondary. And we want to know what core type this is. And it's just good to know the information. Because if we ever have to replace it, the core type is going to be important. So we come back and look at our source. We have 120 volts and we're running at 60 hertz. So now we're going to look through this guy, and the transformer we have, it's designated as T1 for transformer 1. Schematic symbols, you'll see that listed on there as well. And this is a 4-to-1 transformer. So the first thing we need to do is when we look at these guys is we have to determine, okay, what is my turns ratio? Is this a step up? Is this a step down? Or is it an isolation transformer? So when we look at it with a 4-to-1, it's not an isolation because the numbers aren't the same. So that one's easy to look. So we know it's not an isolation. And then we're looking to determine if it's a step up or step down. So it's not isolation. So to determine that, we need to find out if our turns ratio is, where's my erase button? If our turns ratio is greater than 1, it's a step up. If our turns ratio is less than 1, it's a step down. Okay, so remember the formula. So N is equal to the number of turns in the secondary over the number of turns in the primary. And we get that information from right here. So the N is equal to the number of turns in the secondary, which 1 is on the secondary side. So we have 1 over 4. So this is our turns ratio. It's 1 over 4. 1 over 4 is less than 1. So therefore, it's a step down. So what this means is for every 4 volts that we have on the primary side, we're going to get 1 volt out on the secondary side. So we can apply that ratio. So if we have 120 volts and it's being stepped down 4 times, our V secondary is equal to the turns ratio times our V primary. We can also look at that. We have this formula here for our turns ratio. We also have the turns ratio is equal to V secondary over V primary. And we have our turns ratio is equal to I primary over I secondary. So we use this guy, we just multiply both sides by the primary to get the secondary by itself, and this is what we end up with. So we have 1/4 of 120 is equal to 30 volts. So now that we know that we have 30 volts going from here to here. So our secondary voltage from here to here is 30 volts. Now we look at where our resistor is connected to. Is it connected to the entire secondary? Is it connected to a portion of the secondary? So in this case, we look, it's connected to the entire secondary. So the voltage across R1 is 30 volts. So now that we look in our secondary section over here, we're just going to look at it individually as 2 separate circuits. So in the secondary, we have 30 volts being dropped across 1 kilo ohm. Remember Ohm's law, voltage over resistance equals current. So the current we have over here is 30 volts divided by a kilo ohm. That's going to give us 30 milliamps. So now that we know that, we want to look back, okay, how much current is flowing in the primary? Because we have to have current there, we have current flowing there. Okay, so we come back and we look at our next equation. So we have N is equal to I primary over I secondary. We want to solve for I primary, so we multiply both times by I secondary. So N times, so our turns ratio times our I secondary is equal to our I primary. Okay, so now to solve for that, we just plug in our values. So we have 1/4 times 30 milliamps is equal to 7.5 milliamps. Okay, so that's how much current we have flowing in our primary. So we have 7.5 milliamps in our primary with 120 volts. In our secondary, we have 30 volts with 30 milliamps flowing through it. So we can quickly calculate those guys. The impedance that we have in the primary, so we want to take a look back at this, at how much impedance does this circuit see. Okay, so remember our other equation that we have, our Z primary or R primary, however you want to look at it, is equal to 1 over N quantity squared times the impedance of our load. Okay, so let's solve for that. So Z primary is equal to 1 over N quantity squared times our Z load. So we have 1 over 5 squared times 1K. So we have 1 over 25 times 1K. Oops, that's 11K, not 1K. 1K. That gives us a breakdown of let's see. Got my notes all messed up. I'm using two different formulas. So in this case, we don't have to worry about that because we already have these values solved. We can go back through and solve it. But the big thing we want to look at, so just kind of ignore that last thing I said about the Z primary. We know how much is going to be over there because we have the voltage primary, we have the current primary, so we can just use those instead of going back through and reinventing the wheel. So we have 120 volts and we have 7.5 milliamps. We solve those out. And that gives us 16 kiloohms. You can go through the other direction and that'll give us the answers too. But in this case, this is what we wanted to end up with, is we have what impedances our primary seeing basically, and we can just do that by the voltage and the current. There's no reason to go the other way because we already have those values. We only really need to use this one when we have when we don't have anything else solved. Okay, so power in the primary is going to be voltage primary multiplied by current primary. So we take the 120 volts, multiply that by the 7.5 milliamps, and that's going to give us 900 milliwatts of power. Most of the transformers that we have, and especially the ones that you guys took home, those are rated for, I believe, about 10 watts of power, 10, 15, 20 watts of power. So this is well within what it can handle. All right, so after we do that, then we got to look, okay, our phase shift in our secondary. Do we have a phase shift? Look at our phase dots or the lack of phase dots. In this case, we can come back and look here. We have one dot on the top, one dot on the second, so that means they are out of phase. So the phase angle is going to be 180 degrees out of phase, and we can actually measure that on the scope. You plug it into your generator, go through the transformer, plug it out on the secondary, and you will see this phase shift split apart. You'll see that shift. And then the core type is 2 solid lines, so that is iron. So that is basically what we're looking for when we're solving for a transformer. In a few weeks, when we start getting into power supplies, we'll be more concerned with a lot of these guys because we want to make sure we don't blow up the components. When we get to the power supplies, that's really where a lot of the fun of the semester is. It's combining everything together. We're filtering out stuff. We're getting it and creating it to such a point where we can take 120 volts, we just plug it into the wall, we can spit it out, and we can generate whatever voltage we want. And so um, that's going to be kind of the capstone of the semester. And this is where this is all leading to. This is just the little parts and pieces of each of those culminating into how do we put all of this stuff together, and a power supply is how we do that. So anyway, that is the idea, and that's the ideas behind transformers. We use them to step up, step down our voltages to get them to a level that we want. We can use, different applications that way. And like I said, once we get into the power supplies, you'll kind of see the power of transformers being unlocked, and a little bit more, and a little more application. This is just the basics, just so you guys have an idea and understanding of what's going on. The biggest thing that we're going to be using these guys for right now is just simply to step up or step down voltages. We're not really going to be getting into a whole lot of what does the primary see, what does the secondary see, but this is how we do it. We want to give you guys an introduction to it, so next semesters, when you get into them, it's not completely foreign to you guys, and you're like, oh yeah, I do remember learning about this at one time. Now we'll see how they're getting used. So fortunately, there's that, this is just kind of a very brief introduction to them. And then in the later semesters, you guys will see them in a lot more use, a lot more applications, things like that. All right, so that's all I have for this video as well. Again, like I said, any questions, please feel and reach out to me, and I'll answer them the best I can. And make sure you guys get squared away. And with this, you guys should have all the information you need to complete all the quizzes on Moodle. It will give you, you have all the information you need to work on those. So make sure you get through those again. And again, the test is going to be due on Sunday night. I'm working on trying to push these guys back into our normal schedule. So the tests are going to be due Sunday nights. Labs are going to be due Friday night. But this week, we're pushing this back to where the test will be due Sunday, so that'll be back on schedule. But the labs I'm going to have due, not have them due until Sunday night as well. That way everything kind of lines up. You can get everything done over the weekend, and we're going to slowly be shifting back into getting everything done like it was before we became self-isolationists and are having class online and all that fun stuff. And like I said, if you guys do have problems, please reach out to me before, midnight or before 10 o'clock on Sunday. If you're struggling through a section, take the quizzes as early as you can. Get an understanding of what more you need to work on. Please let me know. I still have my office hours available to do Zoom meetings, to do at least a face-to-face that way. You can always get a hold of me through texts. But please, if you are struggling with any of the topics, if something's not making sense on the video, if you just need me to explain it again, or maybe in a different way or something like that, or just need some help working through problems, please, please, please let me know. I will have my normal hours going, so 8 to 11 and 1 to 3. I will have the Zoom meeting going, and it's the one that's listed on Moodle in the notes section. So if you have with that number, you can get on. I'll be here. I can answer the calls, and I can even pull up my whiteboard and I can show you. We can walk through things step by step. You'll kind of have to explain to me your numbers, where you got them, and then usually we can figure out where things aren't making sense or where errors were made, stuff like that. So like I said, please let me know beforehand if you guys are struggling with any of this material. I want to be able to explain it as best as I can to you guys and give you every opportunity to to pass the quizzes, pass the tests, and to get forward, because I want you guys to know this information, and you have to know this information. So please let me know what I can do to help, and I'll do what I need to do. So, all right, guys, that's all I have for now. Again, remember, get a hold of me if you need help, and we will talk to you guys later.